like that. And then we covered sort of 4 possible things that you can get out of these tools right now, right? IDT hooks, interrupt descriptor table, of which we see 3, one of which we know is pertaining to Shadow Walker, and 2 of which we don't actually know what those are from. We would have to go look at them. I'll tell you right now, they're actually from Daemon Tools. That's what it looks like over in Gmer. Over here in Toluca, we can also see similar things. So it's saying, all right, it looks like interrupt E is being hooked. So that's marked as red. And the interesting thing about Toluca is that it's also giving you the possibility, the potential to see if there's inline hooks after the functions. So when you click on any given thing, it shows you a few assembly instructions worth of code there. So those all look like they have the same. Okay, this one has an immediate IRET D, so this one immediately always just returns. That one obviously does nothing. But this shows, you know, some of the possible instructions at the places. So this shows in E is hooked, and if we go down here, I don't know if it's going to show them for 62 and yep, doesn't look like it's detecting that index 62 or index 82. Toluca is not currently showing them as hooked, which is interesting. So this right there is the index field. So hear about that interrupt number 62, interrupt number 82 is the other one. So this one's currently not showing it as well. So that's kind of interesting that getting different results out of each of them. Let's see, the other thing we saw were, well, then we went to the GDT. It's not really a GDT hook. In this case, it's just a backdoor kind of thing. And so seeing the call gates, Toluca can tell you that, but Gmer doesn't. Then we saw import address table hooks, of which there are many listed here, not as many as inline hooks. So a bunch of inline hooks in kernel space, or sorry, IAT hooks in kernel space and user space. We can see the same sort of thing over in Toluca, but let's see, I believe, where do you find these? Oh, right there. All right, so there's IAT tab right there that's going to show you some of the inline hooks. So these are the kernel, sorry, I keep saying IAT, inline hooks. Import address table hooks, here are the kernel ones. And it looks like it actually doesn't tell you about IAT hooks in user space. So you know, there's this back and forth in terms, I mean, we know from you having done your homework and run some of these tools, some of the tools just simply don't even look at this level of stuff, right? And even these good tools, some of them look at, you know, Toluca looks at kernel but doesn't look at user space. So that's kind of why I made that Excel file showing the different detection capabilities of the different tools, so that you can use whatever the best one is in order to look at the system and get maximum coverage. All right, that was IAT hooks, and then we talked about inline hooks, which in Gmer are displayed as the section, process, the module, and then the function, which it thinks corresponds to the specific address where the change was made. Yeah, here's what I was talking about before with this sort of error. So you can see both of these say there's a hook at 7C90DA, C0, blah, blah, blah. One of them it says it's a 1-byte hook, one of them it says it's a 5-byte hook. But since I know that E9 is the first, it's the opcode for a jump instruction, I can tell that, one, since E9 is the thing, two, since they're both at the exact same address, you can't have a 1-byte change and a 5-byte change both at the same address, so it's probably really a 5-byte change, and we got some anomaly going on here with Gmer. But those are the 4 main things we looked at so far. They're the things which we have some knowledge about from the other classes. So now we're going to go on to, well, first I'm going to talk about them from the man-in-the-middle perspective, and then we'll go on to some stuff which rootkits can attack, which rootkits can manipulate, which we haven't seen from other classes. All right, so, well, before I go there, we're going to talk quick about 2 things. Within, so for finding these inline hooks, that was the last thing we talked about, the .text section hooks, for instance. Within WinDebug, there is a built-in command called checkImage. And what this does is it says, take what's currently in memory and compare it to what's on disk. And if there's any difference, then it's going to report it. So this is essentially, this checkImage is kind of looking for inline hooks. It doesn't tell you like if there's any data that was changed, only code sections, but it'll give you a basic description from within WinDebug of whether any code changed from memory to disk. And then there's System Virginity Verifier, which is very much like checkImage, but it's trying to also layer on top of that some heuristics about the nature of the changes. So if you see a jump instruction immediately at the beginning of a symbol, they consider that more severe than potentially some other changes. So this SVV basically just layers on top some heuristics about different categories of changes up to a level where they say, you know, this absolutely is bad. All right, so here's an example of some inline hooks false positives. This isn't all of them, but this is a representative sampling, since I'm not going to be able to go to my VM on my class thing. I'll just give this example quick. So McAfee's HBSS, which is mandated throughout the DoD for host protection, has a HIPS component, host integrity protection, or sorry, not integrity protection, host intrusion prevention system, which is supposed to try to stop exploits. And so this HIPS component, it turns out that if you run Gmer on a system that has HBSS installed, you'll find that it actually places some inline jump instructions into the kernel itself, so nt-kernelpa.exe. For the functions that it wants to monitor, such as connect, port, open process, things like this, it puts a jump instruction which jumps to the McAfee code so that they can intercept and analyze what's going on. And it's very similar to Symantec, for instance, in that sense, but whereas Symantec would go into the SSDT and put hooks there, McAfee is putting inline hooks instead in the kernel itself. All right, so now we're going to talk about things from a man-in-the-middle perspective. This is what happens when you put up pictures of yourself for Creative Commons, which I'm sure someday, hopefully someone will abuse this video and make a great remix of me doing my Shoryuken. So, portrait of the rootkit is man-in-the-middle. I said that most people are familiar with network-based man-in-the-middle type attacks where you poison DNS. I think I was talking to you about this the other day, right? Yeah. So, poison DNS, right? And then when someone looks up a host name, they get the attacker's IP address, and you go to the attacker instead. And maybe you do an SSL man-in-the-middle, whatever. You poison DNS, poison BGP, ARP spoof on your local network, all those sort of things are means by which, when you're going out to resource, instead you get redirected to the attacker, and he can, filter the communications that are going on. He can, you're doing something like Diffie-Hellman key agreement, right? He can man in the middle of that session so that he makes one agreement with one side, one agreement with the other. So the man in the middle is, well, it would be Eve in the classic cryptography sense, but here we're just going to say it's that guy. All right, so, just calling out this man in the middle nature. So if we have a normal intra-module function call, so we have a normal call to our own function within our own module. So code is running along, pushes 1, 2, 3, 4, calls some function, right? When it gets there, it takes this call and it goes immediately to some function and it starts executing some code. That code keeps running until it eventually hits something like a return. The return then goes back up to the next instruction after the call to the some function, right? So that's a normal one, and this is a rootkitted one. All right? The WicketSuiteApp.exe is again running along, calling some function, and instead, when it hits some function, the attacker has placed a jump to, my some stuff, which is, that doesn't work, that's not the right thing. My some bulk. That's probably why I did it. It's too big. Right, so you're running along. The attacker has placed a jump instruction immediately at the beginning of the function he wants to intercept. That calls out to, jumps out to the attacker's wicked DLL.dll. Then it executes whatever code, so this stuff, whatever the attacker wants to do. He does that, and then before he returns to where the original control flow went, he has to take those instructions which he overwrote with his jump instruction and execute them still so that everything still executes the exact same way that it would have originally. So then when he jumps back to some function +5 in order to skip over this jump, then it'll just continue doing whatever it was doing. So by comparison, right, this is, right now, sumfunc is jump and then sub ESP 20, whereas originally it was these 3 instructions. So the attacker basically just takes those 3 instructions, copies them over to the side, overwrites it with the jump instruction, and then jumps over and jumps back. Right. For example, you could use a call. It depends. It depends really on just what the attacker wants to do with keeping everything in sync. But like you say, if you use a call instruction, you're going to put something else on the stack, and you would have to make sure that you'd end up having to remove it anyways before you go back, because if you didn't remove it before that push EBP instruction, then your stack's going to be messed up for the original code. So when the original code starts executing, the stack will be wrong, and that'll cause it to not work correctly, probably. Right, so there's your trig class symbol. It's been a while, I know, but remember putting the little things inside the angles? All right, so this is why this is, fundamentally a man-in-the-middle attack, because, this lady over here is trying to talk to that lady, but immediately the man in the middle gets in the way, he intercepts the communication, goes over to him, and then eventually, he passes the message or doesn't pass the message back to the original person. Okay, so that was intra-module. That's when you're just calling functions within yourself, how the attacker can still get your control to go out to his code. If you're calling code outside, and that should have been clear, this is like an inline hook, right? So an inline hook, you put in a jump instruction or a call, potentially. It depends on what else is going on. But you put in something which redirects control directly into code, overwriting existing code, and probably copying that other code out to the side. All right, so then this is the intra-module function call, which is normally mediated through the import address table. So obviously what we're going to be going towards here is an IAT hook. But a normal intra-module call, you're executing your code, you're running along, and then finally you get to a call that looks sort of like this. It's a call with square brackets saying go to memory at this address, pull the value out, and then call to that as an address, be it absolute or relative. And so what I was trying to kind of show down here is a notional representation of the IAT sitting there still in the wicked sweet app.exe's memory space. And if you look at memory address 40112C, 40112C, there's the address of some function, right? So when you do that call instruction, it goes out to 40112C, pulls in the address of some function, and calls to that function. And that's that arrow number 1, right? So some function executes, does whatever, and when it returns, it just returns back to the instruction after the call. Right? So then, in the case where the attacker is man-in-the-middling this, you can see that down in the IAT, where it should have said, some function, it says mySumFunc, right? So the attacker has gone into the import address table. They know that that call instruction is still going to be pulling that memory, that information out of the import address table. So they know they just have to change the IAT, and then everywhere that you would have called some function, now you'll be calling, the attacker's mySumFunc. And so that goes over to here. The attacker may or may not, this is kind of a conditional thing, but I just showed one possible path. Over here, the attacker may, actually that should be lower probably. The attacker may call the original function, he may not. It really depends, right? So let's say this was something where you're trying to open a file or list a file directory. Well, let's say it's just opening a file. The attacker may not even want to call the original file if he checks you may not want to call the original open file if he checks that before he calls the original, he says, are you trying to open my file? So like I'm Hacker Defender, I always prefix my files with hxdef, and then what I do is basically a regular expression check for every file name that I'm intercepting here in my sumfunc. I will check, does it start with hxdef? If so, don't even bother calling the original thing. Just return back and say there's no such file. Right? And that's how you can hide files from user space like Hacker Defender does. But if it's something that's not my file, then go ahead and continue on and call the original so that I don't have to re-implement that. So it would call the original, it would return back, and it would return back. And so this is very clearly an easy place that you can have a man-in-the-middle type of situation, right? So call to a different function than that actually imported. It goes over to the original if we're going to continue this on, and then it calls back to the man-in-the-middle who may or may not filter the results, and then it goes back to the original rootkits.exe. All right, similarly, normal IDT processing. You get an interrupt in. The hardware consults the IDT register to find the interrupt table, goes to the specific offset in the IDT, and then based on the logical address that is built into the IDT entries, right, that 48-bit address, 16 bits per segment selector, 32 bits per offset. Based on the logical address, it vectors to some code wherever. In this particular case, we're saying it jumps into npkernelpa.exe and kitrap3. There's some code that executes there, and eventually, for interrupts, they are returned from using the iret instruction, and that's just specifically to get rid of the stack frame information that gets pushed automatically when an interrupt occurs. So that's the full flow of an interrupt. This is where there would be a pop quiz audio file. But does anyone remember, just out of curiosity, the difference between ntkernelpa.exe and ntosKernel.exe? Other than you? Someone besides you. Actually, probably not. So go for it.
Isn't it just the physical address extensions?
Yes. So it's the use of physical address extensions. So we talked about that in intermediate x86 class. There's a version of the kernel for, quote, normal paging, and then there's a version for when physical address extensions are used. And physical address extensions, aka PAE, has to be used in order to use data execution prevention, or DEP, which is Windows security mechanism. So, yep, that's correct though. All right, so that was, a normal case, and this is sort of a man-in-the-middle case. An interrupt comes in, and instead the attacker has come in here to the IDT and he's changed it, right? Like in that IDT-E case, where Shadow Walker went in and changed index E so that it points at its code. Then it goes out and it has some code. And then at this point, in this case at least, I explicitly called out that there can be a conditional check where when the interrupt occurs, you can either say, I just want to, immediately return, like I'm going to handle this and it'd be done with it. Or if it wants, it can call to the original interrupt handler. And if it does call to the original handler, then when that thing's done, it will return. So the interesting point here is that, at least in the normal case of IDT hooking, unlike with that IAT hooking, the attacker doesn't get an opportunity to have, quote, results come back and filter any results. But that's kind of because most interrupts are not, passing results back or anything like that. They're handling some event, and usually they keep their data in kernel space. They're not like passing, well, I guess they can pass data back out to hardware, but then they're talking directly to the hardware, for instance. Therefore, there's less of an opportunity for an attacker to interpose on the sending data back out to the hardware. It's still possible, but out of scope for this class. All right, so this again is the thing. Interrupt comes in, goes to the attacker code. Maybe he goes immediately and says, maybe he just handles the interrupt himself, in which case he just returns from the interrupt. Or if he can't handle the interrupt himself, and maybe he was just trying to, for instance, in that keystroke monitor example from intermediate x86, in that case, the attacker wants to get the interrupt just so that he can, reach out and see what the keyboard had been pressed, and then he puts the data back in the keyboard buffer, and then he calls to the original handler so that it gets the keystroke as normal. And when that's done, it just returns. Now, there's a variant you could do with this where you could combine it with inline hooking if you wanted, and of course, there's always plenty of opportunities for combinations of stuff, but I don't believe anything does this in the wild. But if the attacker wanted, for some reason, to get control again before you return back to the thing which caused the interrupt, then he could, for instance, put a jump instruction in later on in the interrupt handler code, so that when it's done and when it would have returned back, the attacker could do this. I guess the reason I would maybe say that an attacker might do this, now that I think about it, is let's say that network processing thing that I talked about before, right? Now the attacker could hook the IDT entry, and the attacker could go out and talk to that NIC card and read in the packet that just came in. But what's a lot easier, instead of like going out and learning the specification to talk to the NIC card, is just pass control onto the original NIC card driver. It goes out and talks to the hardware, reads in the thing, and like I said before, for those DPCs, it'll just like, read it into a buffer and then put a DPC to say, call me back later and I'll process this NIC card, this packet later. If the attacker wanted to use something like this, then he could do it after the normal NIC driver had copied that data out of the NIC card into a buffer in kernel memory and was ready to just say, call me back later. Then if the control goes back to the attacker, then he can go out, find that DPC, and then go read the relevant buffers so he can, manipulate the data before the thing is post-processed, for instance. So
okay, I guess in that case, would they probably just hook the handler and not pause those?
Right. Yep. Exactly. In that case, you could just get away with why do you even need to interpose on this initial thing? If you're just going to pass through and let them read the data in themselves, then you don't even probably need to hook the IDT entry. Maybe you just let it do its thing and put an inline hook at the end. So, but yes, that was just something that came to mind now. So, all right. So, all right. Yeah. Since we're still talking about man-in-the-middle type things, I wanted to just kind of explain the Stuxnet thing in the context of man-in-the-middle. So the key component of Stuxnet was that, well, in my mind anyways, was that the attackers basically reverse engineered the Step 7 development environment. And so this Step 7 was a development environment for writing PLC code, programmable logic, wait, I'm forgetting the name. Yeah, PLC, programmable logic control. Yeah, no, it's not FPGA. Well, damn, I just forgot what that stands for. But anyways, it's the programmable logic on the actual. And I'm blinking. It's on the PLC, which is the industrial control device, which they're saying was used to. Basically, they're saying it was the control logic for the centrifuges in their theory. Right? If their theory is correct that it was targeting centrifuges, and there's this control logic which says how fast you should spin the centrifuge and stuff like that. The point is, Step 7 was where you write code in order to program these devices, right? And so they had reverse engineered this sort of development environment. And they found that, okay, the thing which actually knows how to talk to the hardware is this DLL S7 OTBX GX.DLL. So that DLL there in the middle is the thing which actually knows how to talk to hardware. And the hardware is the PLC. Yeah, that is what that stands for. Yeah, I saw that. Yeah, I saw that as well. I'm pretty sure it's PLC. So, so one point was there were this DLL, this bxdx.dll. There were 109 functions that it exported from the DLL, so we're actually in the export address table. And one technique that it used that we talked about in Life of Binaries is it used export forwarding, which is a capability where you can say in your exports, I don't actually implement this, someone else does. And so what they did was there were 109 exports out of that DLL. The attacker came in and they had a Trojan DLL, and they renamed the original DLL so that it was SX instead of DX. So they took the original DLL, copied it off to the side, named it SX instead of DX. Then they named their own Trojan DLL as the BXDX. And so that means when you click on step 7, the OS loader is going to look around. It's going to say, okay, there's BXDX. It's going to load it into memory. And so for one thing of man-in-the-middling they did was they said, all right, for all of the functions they don't care about, that they, having done reverse engineering, determined, these don't influence the ability to read or write to the PLC. For 93 of those 109 functions which are exported, they just redirected it and they said, look, these are actually implemented in this BXSX function. So the OS loader would just automatically grab the correct original functions for 93 of those functions out of the original DLL. But for the other ones, they implemented the stuff themselves so that they could interpose on it, basically. So they could man in the middle these, whatever it is, 13 functions. And for those 13 functions, they wanted to be able to intercept them in order to intercept data going to and from the PLC so that they could modify it. Right? And so basically, that's how it works. Right? So BXDX over here is saying that that's not me. That's an imposter. It says, shut up, BXDX, BXSX. Oh, and by the way, what's PLC's favorite dish? He says it's Luther Burger before he thinks, no, I shouldn't be helping him. He's just helpless to not help him. But the point is that, the BXDX is impersonating this original DLL down there. For everything that he doesn't care about, he just redirects and asks the original. Right? And the original happily does its thing. But for the stuff that it actually wants to intercept and man in the middle, it implements that and then, changes data on the fly as it's coming back and forth between the PLC and the actual development environment. All right, so now we're just into some references. So read about Hacker Defender, for instance, to find out more about all the stuff it's doing for user space hiding. I think because I won't come back to it, I'll just point out that one of the interesting things about Hacker Defender is that I actually have it set up to hide a port on the system. And most of the tools will not actually show you hidden ports and stuff like that. So, I mean, if you try to connect to the port, you'll see that you can. So there's always that kind of cross-view thing, right? You can port scan something and you can see what ports it says is open versus what ports with the port scanning. But I'm just going to point that out. All right, and this is just all references from the other thing. And I was correct that this SBAP was the application of software-based attestation to a Bluetooth keyboard that has been infected with a keystroke login. All right, so again, any questions on, we really haven't covered anything new. I just basically was showing you the man-in-the-middle pictures. But any other questions on inline hooks, IAT hooks, IDT hooks, or call gates? All right, and we're going to move on to some new stuff. All right, so we make reference to system calls a few times already. I made reference to the SSTP multiple times. So we now need to kind of get on the same page with respect to what system calls are, how they're working, at least on Windows. It works very similarly on Linux for most of the stuff here, but there's plenty of Windows flavors here. All right, so first, just to once again reiterate, system calls and the use of the system service descriptor table on Windows are a means for the kernel to export some API of functionality out to user space. because the kernel is in charge of talking to hardware, and user space can't talk to hardware unless it goes through the kernel. So for things like opening a file, sending packets, displaying video, all that sort of thing is something where you have to go to the kernel if your user space application wants to do it. So we're going to kind of look at every step of the way from user space, starting in, myapp.exe, all the way up through all the various places in the kernel where the control flow goes. And keeping in mind that essentially every single step along this way is a possible place the attacker can intercept control flow, and he can therefore hide things. So in user space, we see IAT hooking and inline hooking and stuff like that. That's why you can have ring 3 rootkits. And in kernel space, that's where your ring 0 comes from. All right. So Bill, can we go to the projector? All right. So we're going to start out with myapp.exe. It's just, any little application which happens to call write file. So it wants to write out a file. And how it does that is, write file is not implemented within myapp.exe. It imports it from some other library. If you go and look at the MSDN documentation, it'll tell you, if you want to use write file, you must import this header. And importing that header causes the linkage to occur such that when you have an actual PE file that gets built, the appropriate imports are going to be made for the appropriate modules. So you start at the call to write file. And this is actually imported from kernel32.dll. And this, again, this is all user space. This is just a thing that happens to be called kernel32. It's not any kernel functionality. So this is a user space DLL that's in the same memory space as myapp.exe. And when this calls to write file, this will have a little bit of setup, but then pretty much immediately, if you were to look at this in debugger, you would see that actually write file is basically completely imported, is completely implemented in some other function called ntWriteFile. And this is also in this one's import address table because it's actually implemented up in the ntdll.field. So there's a little bit of setup here, but it pretty much immediately calls right through to ntWriteFile. Now, ntdll is the thing which understands see, there has to be an agreement between the user space components and the kernel space components in terms of, what is the API going to be? What are the indices for this function corresponds to that function. This function in user space corresponds to that function in kernel space. Has to be some understanding and coordination. So ntdll.dll is the thing which has the OS version specific indices that correspond to kernel functions. So, like I said before, commonly you're going to have EAX used as sort of a selector index, which is going to say, I want this particular function in kernel space. And therefore, there's going to be various hard codes of, move this constant into EAX and then jump into kernel space. And, you'll have one for ntWrite file and that'll have one constant. You'll have one for ntCreate file and that'll have another constant. And so each of the things which are exported, ntdll on a per Windows version basis is going to have this constant is always used in ntWrite file. This constant is, well, sorry, when I say always used, to be clear, for a given version of Windows, ntWrite file is going to have a specific constant. If you go to a different version of Windows, it can have a different constant. And that's, the Microsoft programmer's job is to make sure that the ntdll maps up to the appropriate kernel components so that for a particular function, it always has the right constant so that it hits the right function in kernel space. Is that clear? Or was that a bit confusing? Everyone good there? Anyone want me to do it again? So these other pieces right here, the int2e or the sysenter, that's the actual instructions which are being executed to make the transition into kernel space. So sort of two different ways you can go about it. Either call interrupt, specifically calling interrupt2e, or sysenter. You're not going to really see int2e used on anything anymore. It's, I believe Windows stopped using it as of Windows 2000. But that's the way they used to do it, and now they use the specific instruction sysenter. All right, so that's all I want to say about this for now. Just you call something like write file, it gets you into kernel 32. Kernel 32 gets you into NTDLL. And NTDLL says, you know, here's the appropriate index in order to make it so that when I transfer to kernel space, I'm going to get the corresponding function. Right? And as I said, you can kind of hook these at any number of stages along the way. So, you know, you could do an import address table hook at this level. You could do an import address table hook at this level. You could also do a jump instruction immediately there, or jump instruction immediately there. So I'm not going to list all the combinations, but the hooks at this level are what enable stuff like user space rootkits. And the reason it enables it, again, is because this causes a filtering sort of man-in-the-middle situation where if you're trying to write a file, they can, you know, filter on that and write, you know, the file plus virus infection or something like that to mix malware here for a second. All right, so we're going to look at first the interrupt path for something like Windows 2000. All right, so user space, let's say NTDLL called int2e. Oh, and I guess I should say, you may have seen this type of thing on Linux as well in the past. They also don't use it anymore, but if you've ever seen stuff on Linux where it says int80, that's the equivalent where just Linux said they're going to use int80 to go from user space to kernel space. But back in the day, it was int2e here. All right, so what that does is that, you know, tells the system we want to cause an interrupt. It's going to be a software interrupt. Index 2e, so this will be 2e here. And at index 2e, there's going to be a specific function specified by that logical address. And this is KI system service. I don't know if I have anything else here. Yeah, okay, good. So when that interrupt occurs, it consults the IDT and it says, okay, this interrupt is handled by KI system service, which is in NTOS kernel or nt-kernel-pa.exe. So that thing is fundamentally the code which is going to eventually transition to the correct index of the SSDT for this write file operation you're trying to do. All right, so at this level, obviously we can again place a hook right here. If the attacker is in kernel space at this point, by hooking the IDT, he can intercept this call to KI system service and then be able to see all of these system calls. So if int2e is the interrupt which is used for system calls, it's used for all system calls. And therefore, you know, if he puts a hook in the IDT and if it goes to his code, immediately he reads EAX in his code and says, okay, they're trying to call read file, I care about that. Or they're trying to call OpenSocket, I don't care about that. That sort of thing. So he can interpose at this level as well. Was there a question? I thought I heard someone say. Okay. All right, so coming the opposite direction, and that's not accurate. Yeah, okay, I've still got 2 slides in here in the build slide that are not accurate. I need to remove those. Let's see if I can do that quick. All right, so this is the other path. That was one path. Wait. Oh, well. So this is the other path from where we're using the sysenter instruction specifically. All right, so from user space, ntdll.dll calls sysenter. And you haven't heard of sysenter before. We didn't cover an intermediate x86. We're going to talk about it after we go through all this. But basically, it's something which is an instruction specifically trying to support this type of system call thing so that it's set up in a specific way so that it targets, again, some function in the kernel, which is going to, for instance, read EAX and figure out, you know, which system call is someone trying to call at this moment. All right, so again, we haven't seen sysenter how it works, but there is the possibility of hooking something so that instead of targeting this KI fast call entry, you can change some registers around, and now when user space calls sysenter, it will go to the attacker code instead of the original kernel code. And the reason I was saying that other slide was not accurate is because These are two different ways to get to some code which is going to, read EAX and call the appropriate function, but they're not the same code. All right, so let's say we get into KI fast call entry or KI system service call. Right, so we're now in NTOS kernel. We're in the kernel proper. We're in some function which is the target for this user space to kernel space transition. Now this function is the thing which is responsible for saying, okay, what is user space actually asking for? What system call are they trying to call? So it does a couple of things. First, it consults the thread information. So for whatever thread is currently running, and we saw before on that DCOM slide, we said there's, the kernel control process block structure, whatever it is. It's always pointing, the current active thread. So when this code starts executing, it can find, the current active thread, which is the thing which is calling the syscall. And it has to extract the address of the system service descriptor table. So let's just leave this line off for now. It extracts the address of the SSDT. Now, normally, there's going to be some information in the thread where it either points at one of two symbols, one of two data structures. It'll either point at this KE service descriptor table or KE service descriptor table shadow. That's the normal case. But in some cases, such as the Black Energy botnet, it has a rootkit component to it. That goes in, and for different threads, it will actually say, for this thread, I'm going to point the thread information at something completely different from those structures. An attacker version of these instructions where they've copied some of this information off to their own copy, and they've modified and hooked it independently. So you can have these versions over here, which are the normal things, which look clean, but the attacker can go at the thread level and say, okay, this thread level this thread I want to hook, that thread I don't want to hook. So you can actually have, due to the way that this thread lookup happens, you can actually have finer granularity. Now, none of the stuff in this VM that I gave you, anything that hooks the SSDT hooks it everywhere by just changing these tables. But I just wanted to point this out because right now I don't have a good way of showing this in my slides. I'm still working and figuring out how best to show this to let it flow with everything else. But I just wanted to make you aware that later can look for that. Most things can't look for that. Gmer can't look for that. Toluca can't look for that. But one of the things we'll see later can say, does this thread point somewhere other than those two things? Because the thread should always point at one of those two things. But if they don't, then that can be indicative of, well, that's definitely indicative of something bad going on. All right, so anyways, normally the thread information will point at one of these two structures. And these are going to be used to look up the actual table of functions. Skip to it. These two data structures are going to be used to look up that big list of function pointers which attackers can modify. All right, but the other component of this is that this thing's job is to parse EAX to find a particular table entry. All right, and how it does that is like this. So this is me basically blowing up one of those entries over here. So these things right here, you can think of it as an array of 4 structures. So that's why there's 4 elements in each of these. Each of them is an array, and each element of the array is actually a structure. And so this is me blowing it up, and for only one of those entries, filling in the actual structure definition. All right, so this is the blown up version of one of those structures. It's the first one, K service descriptor table. This is what we'll call the normal SSDT, for instance. And unfortunately, some of this is sort of ambiguous in that sometimes we'll call this the SSDT, and sometimes we'll call this other table the SSDT. So unfortunately, that's always going to be ambiguous. All right, so what I wanted to say here is when the function is parsing the EAX value, it parses it according to this entry right here. So it takes the first 12 bits, and it's going to treat that as an index into this table that I'm going to show next. But for right now, all we care about is these 2 bits, bit 13 and 14. And these 2 bits of EAX correspond to which entry out of those 4 entries is going to be used for the next lookup. So you start with those 2 bits, and you index at offset 0 for offset 1 or offset 2 or offset 3. And that's pointing you at one of those 4 structures here. Right? So take those 2 bits and you go here. All right. Once it says, once it decides I'm going to use this, then what it does is it consults this service table base entry of the thing, of the system service descriptor table, which unfortunately that's the name of the struct. Consults the service table base, and the service table base is a virtual memory address where it says here's the start of some big array of function pointers. So everything in that table up in the upper right-hand corner, that's just a 32-bit function pointer. And so it goes, these 2 bits say index 0 here, and then these 12 bits say index whatever in that table. And so in this particular case, it was, 0 here, and then 112 here. So index 112 up there is nt write file. So that's the kernel side implementation of the function nt write file. Let me see if I have anything else. So then what happens? Yep, so that points at that. And so having found this, your, whatever the name is, again. All right, so this is, again, KI system service or KI fast call entry. They're parsing this EAX, looking at that data structure, and when they finally find that entry, then they're just going to jump to that entry and start executing the code there. So it's parsing this, it's going to that table, and then it's going to that table. And when it finally gets that address, it's going to immediately take that address and jump there and start executing that code. And that's how the kernel side of things goes and finds the actual function which is responsible for the implementation of the thing which was called way back in myapp.exe. When it just said, I want to do a write file, it has to follow all this path in order to eventually find the thing which actually knows how to talk to the hard drive and all that sort of thing. Although, in reality, there's more levels of abstraction, but we'll just pretend that function goes and writes to the hard drive. All right, so, yep. Eventually, KI service, whatever, calls this, and then it jumps to the actual implementation in NTOS kernel or NT kernel PA. And so this is, again, this is a new thing where where the attacker can hook stuff. He can go into this SSDT, this system service descriptor table, and fill this in so that instead of pointing to that, it points to the attacker code down here, and then the attacker code points up there. So this is just yet another man-in-the-middle opportunity waiting to happen. And similarly, like I said, I'm not putting all possible combinations, but the attacker could leave this unchanged and go to this and put a jump instruction there, which jumps out to his code and then jumps back to that code. And those are the sort of things which we saw back in these were the things that I had pulled from, some previous people's slides and stuff, right? That's the kind of thing they're saying. So this is the, this is the KI fast call entry, or this is the KI system service, right? So they're saying, user space calls to that thing parses EAX to go to there. That goes to, okay, now it goes to rootkit instead of going to there. Right? It should have went to NT kernel write file or whatever, but instead it goes to rootkit. Or, right, let's say it did go to the original location, then it can get redirected to rootkit and back. Okay, so that's kind of the full path now from user space to, through a couple of DLLs, up to this sort of multiplexing thing which just parses EAX and goes to the right function, and then eventually the function. And there's many places to hook along the path. All right, and so I just want to show sort of the equivalent of that. So back here, I said there's 2 possible tables, right? So one of them is going to be used in some cases, one of them is going to be used in other cases. So I said in the quote normal SSDT case, it's probably going to be using that first table. So now I want to talk about that second SSDT case where it uses the second table. So in this second case that we're going to talk about now, eventually this, well, I didn't leave this in. I should probably put that in again as well. I want to put that in. All right, so this second case has to do with when code is using GUI functionality within Windows. So in order to speed it up, Windows implements most of its GUI functionality as a component of the kernel. So these things like, drawing frames. I mean, it kind of makes sense, like I said before, in order to write to the videos, to write to the actual screen, you're going to have to go through the kernel anyways. And so it's really just a question of whether that processing occurs in user space or kernel. Yes. So I think some of this right here is that I just added this between when those things got printed. So in this particular case, something is going to call a GUI function. I guess I picked update colors. So there's something which is going to update colors. That calls into GDI32. And now I need to write what GDI stands for. I think graphic device interface, maybe, is what GDI stands for. Doesn't matter, it's close enough. Graphic device interface has update colors, but very similar to that case where we had kernel 32 and NTDLL. It turns out it's all just sort of implemented within this one module. So you call update colors, but in reality, this thing is just sort of a pass-through to eventually call NTGDI update colors, which does the same sort of thing where it's going to take a hard-coded value, put it into EAX, and then call into kernel space through whatever mechanism. All right, so it calls into kernel space. Yeah, I can put that. That's all good. Now I said, so specifically in the case where a function is known, when a thread or process or thread, if a thread is going to use the GUI functionality, what happens is the kernel goes in there, and I said in the thread information on a per thread basis, it either points at that one or that one. But the first time that something's going to use GUI functionality, the kernel goes in and updates this thread information to say, okay, you're using that one. So I said the normal case points there, but for anything which is going to use graphical functionality, its thread information gets updated to point there. And so if we kind of look at this, just diffing between those two, they look exactly the same, except that one has index 1 filled in, and that one has it unused. Right? So index 1 is win32k.sys. This is the thing which actually implements the kernel side of the GUI functions. For the first entry, the 0th entry, that native API, that's actually the exact same thing. That'll have the same data as the other one. It's basically just a copy of that structure over there. So now we're talking about something that called GDI. GDI called into the kernel. In the kernel, in let's say ki fast call entry, it looks up the thread information, and that says it's pointing at AE service descriptor table shadow. So this is what we sometimes call the shadow SSDT. So if you have any tools which say your shadow SSDT is hooked, it's saying we went to that thing and looked at its tables and they were manipulated. So for the shadow SSDT, the use of it is sort of implied by the fact that you have a different constant here. So we saw in user space side, it moved the constant 112e. And when you parse that down, what you see is that 1 makes up these those top bit 13 and 14 there. And so that one is used as an index into this, and that's why I blew up that structure this time, right? Last time I blew that structure up here. But this time 1 says, we're going to go at, offset 0, offset 1. And now we're going to consult that data. But now we're just going to do the same thing as last time. We're going to check that service table base. Service table base has a virtual address. That's a pointer to the start of an array. And at that array, then we just take these last 12 bits, the 1 to E, and that's an index into that, which is where we find the actual implementation of NTGDI update colors. So, but NTGDI update colors is in the win32k.sys module. So that previous SSDT, everything was implemented in NTOS kernel, NT kernel PA.exe. This SSDT, the shadow SSDT, everything is in win32 k.sys. So they work exactly the same, but the point is, in something that doesn't use the GUI functionality, this 0th entry right there is not filled in with anything. So if you were to try to, call some function that had, if you were to say you're feeling clever and you think, oh, well, I understand how ntdll.dll works, or I understand how GDI32 works. I want to just manually call this function now. Right? You could manually put a number in EAX, and then you could manually call sysenter, right? And you would end up at that function which parses this, and it would go there and it would find, potentially a null value, and it would add null to, offset, and then it would try to call to that function, and then you'd crash, right? Well, I mean, it won't let you blue screen the box or anything, but at least I don't think so. I hope not. But essentially the point is, you can't use this unless you're in the context of a process for which this is valid and which Win32K is mapped in. So that's another interesting thing, is that even in processes, in some processes, if they're not using the GUI capability, this Win32K is not even mapped into its virtual memory space. So you wouldn't even be able to see it anywhere. And that's another reason why it would potentially crash. All right, and then again, you get to this shadow SSDT. That can be hooked as well. And then that eventually goes into the Win32K. All right, so this is the big picture here. We start at myapp.exe down in user space, right? That calls some DLL. Maybe we're just going to go for the quote normal SSDT case, right? That calls to kernel 32. Kernel 32 calls to ntdll, which is the thing which actually implements the transition from user space to kernel space. I'm just going to follow this sysenter side of things. Sysenter calls to ki fast call entry. It should always be pointing there. This thing breaks up whatever EAX you gave it, and then it says, okay, for the current thread, it's either pointing at that table or that table. And we're going to say this is the non-GDI case, so it must be pointing at that top table there. That's the normal SSDT. And so you put in, EAX, and it's maybe 0112. Yeah, 0112. That was the example. And so 0 means, yeah, this is why I need a pointer. Zero means index 0 into this thing, right? Index 0 into there, and then index 112 into the table that it's pointing at. And that SSDT table for this thing at index 0 is always going to point somewhere in NT, which is the shorthand for NTOS kernel.exe, etc. So all those entries should always point at NT. And all those entries should always point at Win32K.sys. So that's sort of the flow there. One way or another, you're getting to either, in GUI things, you're going to Win32, and in normal system calls, you're going to NT. All right, and I don't know about you, but when I look at this, let's see. Well, see, it ruined it because I was hoping it wouldn't be on a page boundary. But when I looked at this the first time, I said, okay, that is clearly a dinosaur jockey, right? I mean, it's just obvious, right? But I said, no, it's not a dinosaur jockey. OMG, it's Yoshi. And Mario's doing the splits. Right? See, it's an ink blot test. Thank you for your pity chuckles. All right. So that was the big picture overall thing. So now we said there were at least 2 new places that we saw the hook in that case. We said sysenter can be manipulated to point somewhere else, and the SSDT entries themselves can be manipulated to point somewhere else. So sysenter would have been a great thing for the intermediate x86 class because it pertains to these other things called model-specific registers, but wasn't enough time. That class is already a bit full. So yeah, I kind of already covered basically all of this. This is just reiterating that, as far as I'm concerned, I'm pretty sure that the call gates were originally there to support this mechanism. a call gate in the GDT, the whole point would be, you would have a call gate that just says it targets right here, right? And so from user space, you'd just do call to this call gate. It would go there, and it would check EAX and stuff like that. That probably has more overhead to use a call gate, probably has more overhead to use an interrupt. So that's probably why we ended up with interrupt-based things to start with. People just probably did performance checks on it, said, well, interrupts are faster. I'm just going to go with interrupt rather than call gate. And then even beyond that, eventually people said, well, even interrupts are not necessarily that fast. There's still a bit of overhead that's unnecessary there because of the checking against permission levels and stuff like that. We know that using interrupts are a general mechanism where they can transfer to different rings and stuff like that. But you're basically always going from ring 3 to ring 0 with this int2e, right? You're never going the opposite way. So in order to support this, Intel added the sysenter instruction. And this is really just to support system calls. So just FYI, this has a different name on AMD. So this is the syscall / sysret. Right? So it kind of makes more sense there, syscall rather than sysenter. But I'm pretty sure Intel already has a syscall instruction that relates to virtualized systems and things like that. So anyways, on Windows greater than 2000, you should see syscall or sysenter being used. And same thing with Linux systems greater than or equal to Linux 2.5. So how the syscall instruction works, sysenter, I gotta keep going to sysenter. How the sysenter instruction works is that there's these things called model-specific registers. So the type of registers that we talked about in the other classes are your general-purpose registers or maybe your control registers and things like that. The model-specific registers are meant to support features which may be specific to, in the name, may be specific to a model. So, if this model of chip has hyper-threading support, but this one doesn't, maybe you have an MSR, that, controls or tells information about the state of hyper-threading on the system on one versus the other. But that said, there ended up being certain MSRs which are, they called them architectural MSRs. I don't think I put that on there. Yep. So eventually they used some of these miscellaneous MSRs. They used them for functionality like this sysenter such that they can't really get rid of it in future things. It can't just be like you use it on this model but not others. And so they became, quote, architectural MSRs. So they're basically just added registers where they're used for one specific purpose, but they should pretty much be there all the time. And so in the case of sysenter, there's multiple names for this, but this is this is the architecture MSR name. Things that start with IA32, that's where they're trying to tip you off and say, like, this is the mnemonic for something which should pretty much be here all the time now on Intel 32-bit systems. So IA32 sysenter EIP, this is just a mnemonic for, if you were programming something, this would just be a macro. It's just saying this name corresponds to this number, 176. So in reality, the MSR that holds this particular thing is MSR 176. And you read and you write from MSRs of a given number using the read MSR and write MSR commands. So if you want to go out and you want to see where this particular MSR is pointing, and this is another thing I was supposed to add. If you want to see where this is pointing, you go issue the read MSR command. You set, I think it's, this is what I'm going to go right at the next break. You set ECX equal to this 176. You issue read MSR, and whatever comes back in the EAX register is the value that this MSR is holding. So I'm going to leave it right there, and then I'm going to whip together a slide on that to make it more concrete. So let's do a 5-minute break here.